See, this is your first year of engineering, and I know that you're all excited. I'll talk about a branch of civil engineering today. I really enjoy civil engineering and what it offers to the community in general. So, what is geotechnical engineering? Geotechnical engineering and engineering geology are a branch of civil engineering that uses scientific methods and principles of engineering to collect and analyze the physical properties of the ground for use in building and construction. Geotechnical engineering utilizes the discipline of rock and soil mechanics to investigate subsurface and geologic conditions. These investigations are used to design and build foundation, earth structures, and pavement subgrades. All the projects typically require geotechnical investigation prior to starting a project. For example, roads, bridges, high-rise buildings, condo buildings, plants, commercial buildings, etc. So geotechnical report means different for different audiences. For example, owner or developer. A lot of times the owner engages a geotechnical engineer in pre-purchase stage, or if he is buying a property to building a, for example, mixed use high-rise or 5 to 6 story condo building, etc. Geotechnical engineers perform the investigation to give the owner indication if the site is buildable or outline what the challenges are. Architect. A lot of time, the developer or owner hires an architect to manage all the other consultants. And architects are also looking for similar information what the owner is looking for. Can we build the structure that we want to build in this particular land? Engineers, especially structural or municipal engineers, require data from a geotechnical engineer to design. Contractors. It is important for contractors to understand what type of cut and fill would be required to balance the site. Do they have to bring in fill and what the volume is, where the water table is prior to bidding on a project? Municipality. All the new development permit requires geotechnical report. The municipality want to make sure that if the land is close to the slope, the slope had been assessed, it's safe, and what the setback area is, etc. Geotechnical, typically a client of the geotechnical firm sends out a request for a proposal, and geotechnical come up with scope like how many holes, what depth, how many samples, SPT at different depths, and the cost to complete the investigation. So when a proposal is accepted, the geotechnical engineer go to work. First thing the geotechnical engineer do is place first call, or we have in Alberta, it's called call before you dig service. Or some cases, we need private locates to make sure that the area that we will be drilling is safe and hazard-free. And then the geotechnical engineer designs the field work. For example, it says, oh, okay, based on what the land would be used for, they say, okay, we'll do, for example, 6 boreholes to 9 meters. We're going to install 2 standpipes to 9 meters to monitor groundwater table. And they also design, for example, what type of lab tests they'll be doing. For example, basic tests like moisture test, outer work limits, hydrometer test, etc. The report will cover the site condition, foundation design parameters like piles, footing, screw piles, etc. The report will also address earthwork, grading, parking lot, and construction monitoring basics. There are so many different types of drill rig used around the globe to collect information below the surface. Here are the few common drill rig pictures that you see that were used in Canada. We're going to show you a video now how this drill rig is used to collect samples below the surface. Hope that you'll enjoy this video. And if you have any questions, we'll take those after the video has been completed. All right, here we go.
The four most common drilling techniques: solid stem augering with the open hole method, hollow stem augering method, the wash boring method, and the casing method. It will also cover the basics of pushed and driven samplers. There are a number of types of drill rigs available. Some of the most common are large truck-mounted rigs, sometimes called highway rigs, off-road track-mounted rigs, and trailer-mounted or portable rigs. Different rigs are suited for different site conditions and different drilling and sampling methods. The large truck-mounted rig is the most versatile and one of the most common drill rigs used. However, it can only be used in situations where it can be driven onto the site. The process of drilling is similar regardless of the type of drill rig used. First, we position the rig over the location where we wish to drill. Then we erect the drilling boom or mast and make sure it's vertical. A drill head mounted on the boom is the mechanism used to perform the drilling and sampling operation. The drill head provides two motions to aid in drilling. A torque can be applied to rotate the bit, and a vertical thrust can be applied to raise and lower drill bits and other equipment. There are many different drilling and sampling techniques we can use to investigate the subsurface conditions. One of the simplest is the open hole method using solid stem continuous flight augers. The flights on a continuous flight auger run the full length of the auger. At the tip of the auger is a cutting bit. The inset photo shows two different diameter solid stem augers with two different types of cutting bits. The auger is rotated and pushed into the ground by the drill head. The bit at the tip of the auger loosens the soil at the bottom of the hole, and the flights carry the cuttings to the ground surface. An engineer or geologist can estimate when new soil layers are encountered by observing the changes in the cuttings as they're brought to the surface. These cuttings can be collected as bulk samples. However, they are low-quality samples because they're completely disturbed by the cutting process and because soil from the upper layers can contaminate soil from the lower layers as the cuttings are carried up the auger flights. When the boring reaches a depth where a higher quality sample is desired, the auger is removed from the hole to make room for the sampling equipment. In this method, the borehole must be able to stand open without support, which is why we call it the open hole method. When we wish to take a sample, we replace the auger bit with a sampling tool or sampler. Nearly all soil samplers consist of some sort of hollow tube which is inserted into the soil to retrieve the sample. There are many different designs of samplers to suit different soil conditions, but the basic process of sampling is similar for most of these samplers. The sample tool is lowered to the bottom of the boring and then pushed into the soil below the bottom of the boring. When the sampler has reached its full depth, the rods are twisted to shear off the bottom of the sampler, and the sampler containing the soil sample is retrieved from the boring. The sample is then stored for later analysis and testing. The sampling tool is replaced with the auger, and the auger lowered back down the hole. Augering continues until we reach a new layer where we wish to take another sample. The auger is then retracted from the hole and replaced by the sampling tool, and another sample is taken using the same process. When the soil is very stiff or dense, it's not possible to use a push-type sampler. In these circumstances, we use a heavy walled sampler that can be driven into the soil using a drop hammer. The process is similar to retrieving a push-type sampler, but uses different equipment and a different sampler. The open hole method only works if the soil is stiff enough and strong enough to remain open after the augers are removed. While it is often possible to use the open hole method, many times the soil is not able to maintain an open hole for sampling. If the soil is soft, it may squeeze into the boring when the augers are removed. This often happens in a soft clay layer. If the soil is a clean sand with little or no cohesion, the soil at the sides of the hole may cave or fall into the boring. This is particularly a problem when drilling in sands below the water table. When squeezing or caving conditions occur, we must use a different drilling method that will support the borehole during the sampling process. One method that can be used in caving or squeezing soil conditions is the hollow stem auger method. In this method, we use a continuous flight auger as in the open hole method, but in this case the auger stem is hollow. The bit in the center of the auger is retractable and can be removed through the hollow stem. The inset photo shows a hollow stem auger and its retractable center bit. For illustration purposes, the center bit has been removed and is shown next to the hollow stem auger. During drilling, the center bit is inserted inside the hollow stem. The augering process proceeds in the same fashion as with the open hole method. When we reach a depth at which we wish to take a sample, we stop augering, detach the center bit from the auger and remove it.
All right. Anybody have any questions at this point? Okay, we'll go to the next video. If you choose to be a geotechnical engineer or a civil engineer, typically you would be doing what I just showed you, but I just showed you an animation, but from this is the video that we will show from a field engineer's point of view what the drilling experience is. Anyway, here we go.
My name is Pearson Holt. I work with Building and Earth Sciences as a field engineer. We're out here in Fountain Heights drilling for road improvements, new traffic lights, new light poles, and a raised median in the middle. So Lee and Terry behind me are currently sampling soil. We sample every couple feet, and what is going on right now, that's a hammer, it's a weight, it's a 140-pound weight, and we know how far it drops, so we can reference that to how hard or soft the soil is, give them, the structural guys, a report, and that'll base their foundation design off our report. So this rig is a CME 75, and what we have are hollow stem augers. The hollow stem, they're hollow in the middle, so we drill down to the depth we desire, and then we put a rod in it, a spoon, it's called a split spoon, and we put the hammer on top of it and count how many blows per 6 inches, and we come up with the end number from that. For roadways, it's different. You can get away with softer soils depending on the traffic. Maybe in a parking lot, it can be softer. Depending on how much weight's going on these light poles and how big they are, we usually stop somewhere 8 to 12 is pretty good soils for these. And that's kind of how it always depends. Every area you drill is a little different, even if you're in the same formation. It's not boring, but it's boring. Every day's an adventure at Building and Earth Sciences.
You guys can hear the sound of the video and everything properly?
Yeah.
All right, perfect. So after the field investigation is done, during the process, we collect samples and we bring it to the lab. And in the lab, we do some basic tests. We do, for example, moisture content. Typically, moisture contents are done on almost all the samples. outer bag limits, geotechnical engineer typically decides how many outer bag limits they will need the lab to perform after they review the borehole logs. Hydrometer, typically, again, engineer of record performs this test to find out particle size distribution of fine-grained soil. Grain size analysis, same thing. They want to know what the particle size distribution of a given soil sample is to make some recommendations. Also, the other test done is California Bearing Ratio Test, or CBR. It's a penetration test used to evaluate the subgrade strength of roads and pavements. Then we also do sulfate test. Sulfate test is done to see within what type of challenge you will have with the soil and what type of cement should be used in the concrete mixes. So moisture content test is very basic and required for almost all the samples. So this video will show you how we do it in the lab setting. Now, if you work or your summer jobs, you would be doing this type of test on a regular basis to just understand the soil, the classification, and what type of moisture you see. And also through your junior year, you would be doing this. Here we go.
Zero the scale and place a clean, dry sample container with the lid on the scale platform. Record the tin number and the tare or empty weight of the container, including the lid. Obtain a representative moisture content specimen and place it in the sample container. Immediately cover the tin with the lid. Zero the scale and place the sample on the scale platform. Record the tare plus wet weight of the sample. Remove the lid and place it below the sample container. Put the sample, container, and lid into the oven. Dry the sample to constant mass at a temperature of 230 plus or minus 9 degrees Fahrenheit. Constant mass means that the change in mass is less than 0.1% after 1 hour of drying. If the sample contains gypsum or has a high organic content, dry it at 140 degrees Fahrenheit or use vacuum desiccation. Remove the sample, container, and lid from the oven. Immediately place the lid on top of the container to prevent the sample from absorbing atmospheric moisture. Allow the sample to cool to room temperature. Zero the scale and place the cooled sample container on the scale platform. Record the tare plus dry weight of the sample. Calculate the moisture content by dividing the difference in the wet and dry weights divided by the dry weight and report to the nearest 0.1%. Note that for soils, the tare weight.
So that's pretty basic and straightforward, very simple task that you would be doing in summer jobs or your very early stage. Even when you go, I think you go to second or third year, you would be doing some in different universities would have lab, and you would be doing these tests, which includes this hydrometer test that we would be showing the video for. Enjoy.
So this week we covered particle size distribution, and we used a hydrometer method to determine our texture of our soils. Okay, so what you did in lab this week is that you put 50 grams of soil into this shaking jar, and we added sodium hexametaphosphate. So sodium hexametaphosphate acts as a deflocculant, so it breaks up those soil aggregates so the sand, the silt, and the clay aren't bound to each other in aggregate form. And that way we can get more accurate readings in our sedimentation jar, because if they are aggregated, things will settle out faster than we want them to. So we really want to coat all of the soil particles with SHMP. So here we'll add 25 mils of SHMP. And now we're going to add 100 milliliters of water to this jar. So in here we have our soil, the SHMP, and 100 milliliters of water. And now we need to shake it vigorously for 3 to 5 minutes. Time. Okay, so now that we have vigorously shaked our solution, we're now going to add it to our sedimentation jar. So we'll take the plunger out, add our solution to this sedimentation jar. You want to be sure whenever you're doing this in the future that you rinse out the inside so that you want to get everything from your shaking jar into your sedimentation jar. Now we're going to use a plunger to resuspend everything in the sedimentation jar. And then as soon as I take this out, Amy is going to set in the hydrometer and time for 40 seconds. 40 seconds. That's our reading. This reading gives us the percent of silt and clay that's in solution. Because after 40 seconds, the sand has settled out, and only the suspended clay particles and silt particles are what are pushing up on the hydrometer. So this reading we will use in our future calculation. Our next reading is at 1.5 hours. So we'll see you at 1.5 hours. So it's been 1.5 hours. So what we expect to be suspended is the clay, whereas the silt and all the sand particles have settled.
You saw that how the ladies were having so much fun. It's actually fun to do this test. So hopefully you guys get to enjoy this if you choose to be a civil engineer. The next one that we will show, again, another lab test. It's done on a regular basis. Yeah, you would be doing as a summer students and as an EIT. It's called Outerberg limits. Here we go.
Outerberg limits. The Outerberg limits describe a soil's reaction to water content. The Outerberg limits were created by the Swedish scientist Albert Outerberg in 1911. The limits can be used to classify and estimate the mechanical properties of a soil. The following tests show methods into determining the water content at the Outerberg limits and works for cohesive soils including clays and silts. The two limits of interest for the following procedures are the plastic limit and the liquid limit. The plastic limit describes the water content at which the soil transitions between a continuously deformable plastic state and a more rigid solid state. The liquid limit describes the water content at which the soil transitions between a plastic state and a flowing state. Procedure. Determining the plastic limit of a soil has not changed since the first time these tests were described by Wintermeyer in 1925. This test requires only the soil to be tested, a glass plate, and a tare to hold down the soil sample. First, the mass of the tare must be recorded. Next, to determine the plastic limit, a small handful of fine-grained soil is wetted until it is smooth and plastic. This mixture is then rolled on a glass plate using one's palm until the soil is about 1/8 of an inch in diameter. The soil is then rolled up into a ball, and the process is repeated until the soil begins to crumble before becoming a thread. The soil is then placed in the tare and is massed and dried in an oven of no more than 140 degrees Fahrenheit, and then massed again to determine the water content of the soil at the plastic limit. Determining the liquid limit of a soil has not changed since 1925. The test described here was created by Arthur Casagrande. Along with the soil to be tested, this test requires a brass cup apparatus with a crank that lifts the cup 1 centimeter and drops it repeatedly. This test also requires a grooving tool. First, a tear is masked and recorded. Next, a sample of the soil is wetted until it is about liquid. Next, about a 1/3 inch sample of the soil is placed into the brass cup. Using the grooving tool, the soil is scored down the middle, and be sure to follow the cup's curve cutting deep into the brass. Next, using the crank, the cup is lifted and dropped at about 2 drops per second. The groove between the soil should close after 25 to 35 drops. If the groove closes before 25 drops, it is too wet. And if the groove closes after 35 drops, it is too dry. The water content must be changed. Once the groove closes between 25 to 35 drops, the soil is collected into the tear and masked, dried in an oven, and masked again. Finally, the water content is found at the liquid limit. Atterberg limits, calculations, and analysis. The outputs of these tests are water content and the soil's behavior. These values can be used to find a number of engineering properties such as plastic limit, liquidity index, and plasticity index. These properties describe how the soil will react to the stresses subjected to them. Common sources of error. The most common source of error for the Atterberg limit test come from human error. For the plastic limit, pressing too hard while rolling or not adding enough water initially can lead to erroneous results. Using too small of a sample will also distort the water content calculations, which are vital to this experiment. For the liquid limit test, errors can result from the wide range of drops that define the liquid limit. Ideally, one should get the groove to close to exactly 25 drops, but due to the trial and error nature of this procedure, achieving the correct number of drops is difficult and time-consuming. Also, the brass cup must be correctly calibrated for the test, having a 1 centimeter drop. A height that is greater or less than 1 centimeter could lead to erroneous results. Dragging the grooving tool can also disturb the soil sample and lead to an early or late closing.
Important section of a geotechnical report. It should definitely have project description and site conditions, investigation procedures, soil conditions, lab test reports, groundwater conditions, frost level, foundation recommendations, shallow foundations such as footings, deep foundations such as piles, screw piles, pavements, earthworks, radon considerations. The pavements typically have a few options. For example, light duty. It could be light duty structure or heavy duty structure. These are general description with actual loads estimated. Other projects such as highway should have design criteria specified, such as equivalent single axle load or ESAL, and vehicle weights like per Alberta Transportation, ASTO, ACI. Different county has different specification. City of Edmonton, for example, have design and construction and standards. And Fort McMurray, Ute Buffalo would have also their own standards. Earthworks. Mostly the section provides recommendation for stripping, subgrade preparation, dewatering, fill material, moisture compaction specification, and also maximum slopes. Higher compaction efforts may be needed to limit settlement of deep fill zones. Now, once the geotechnical reports are written, the job of the geotechnical engineer is not complete. So geotechnical engineer stays involved with the project throughout the construction phase. they make sure that the project is constructed per geotechnical recommendations. Foundation is the most important part of a structure, as you all know. There are many types of foundation that are used for a building, high-rise, condo, commercial buildings, and mine sites. If the foundations are not installed properly, the structure have high probability to fail. Over the next few videos, we'll show you different type of pile foundation installation. Please feel free to ask questions. These are pretty, I find it very interesting videos, and you might have different questions. So feel free. For example, this is a look at this monopile. This is like some of these monopiles are 10 to 15 millimeter in diameter. Sorry, Neil, is there a question?
Any questions? No, watching the tests.
Okay.
Hey, what's always interesting is it's not like a precision experiment to design, say, with chemistry or physics or anything, but what it is you're dealing with real materials here out in the world. So it's engineering, but it's kind of a different level, I guess, of precision that you're working with here.
Yep, and it can be this engineering is so exciting. It can be modified based on the conditions on site, based on the needs, based on the schedule. We modify it on the fly, on site. So here's a video of different type of piles. A pile is basically a long cylinder of a strong material such as concrete that is pushed into the ground to act as a steady support for structures built on top of it. Geotechnical engineers design and monitor these piles installations.
Foundations provide support to the structure, transfers the loads from the structure to the soil. But the layer at which the foundation transfers the load shall have an adequate bearing capacity and suitable settlement characteristics. Types of foundation are mainly divided into two types, and they are shallow and deep. So here pile foundation comes under deep foundations. Here you can see different types of pile foundation listed based on their construction, function, and material used. Let us see each type in detail. First one. Driven or displacement piles. Which are driven are termed displacement piles because their installation methods displace laterally the soils through which they are introduced. Installation techniques. Dropping weight. The dropping weight or drop hammer is the most commonly used method of insertion of displacement piles. Second one. Replacement piles that are formed by creating a borehole into which the pile is then cast or placed removed as part of the process. These are also known as bore piles. End-bearing piles. In this type of pile, the loads pass through the lower tip of the pile. The bottom end of the pile rests on a strong layer of soil or rock. Usually, the pile rests at a transition layer of a weak and strong layer. As a result, the pile acts as a column and safely transfers the load to the strong layer. Friction piles. Friction pile transfers the load from the structure to the soil by the frictional force between the surface of the pile and the soil surrounding the pile, such as stiff clay, sandy soil, etc. Compaction piles. These are used to compact the loose granular soil, thus increasing their bearing capacity. The compaction piles don't themselves carry load. retention or uplift piles. These piles anchor down the structure subjected to uplift due to hydrostatic pressure or due to overturning moment. Anchor piles. These piles provide anchorage against the horizontal pull from sheet pulling or any other pulling. Batter piles. These piles are used to resist large horizontal or inclined forces. This type is adopted in sea-shore structures. Fender piles. These piles are used to defend water from structure against impact from ships or any other floating objects. Sheet piles. These are sections of sheet materials with interlocking edges that are driven into the ground to provide earth retention and excavation support. Sheet piles are most commonly made of steel, but can also be formed of timber or reinforced concrete. Sheet piles are commonly used for retaining walls, land reclamation, underground structures such as car parks and basements, in marine locations for riverbank protection, seawalls, cofferdams, etc. Concrete piles. These piles are made up of concrete and are further divided into precast piles and cast in situ piles. Steel piles. These piles are made up of steel with different sections like H. Timber piles. These piles are generally made up of wood material. This type of piling system is widely seen in offshore structures. Composite piles. These piles are unique as these piles are cast with the combination of either steel and concrete or timber and concrete.